All right. Hello, everyone. I'm Dhruv, and I'll be presenting this paper on rapid exploration for open world navigation with latent goal models. This is joint work with my colleagues Ben, Nick, and Sergey. So let's say I tell you I'm hosting a party tonight after the conference at my rental home in South Kensington, and I send you the address and a photo of what my house looks like, which I took this morning. You're excited to join, because of course. But you realize when you get off at the tube station that you don't have battery. And motivated by the great networking opportunity at the party, you're determined to look for a way to get to my house, which is somewhere in this mess. You might take a few wrong turns, you might go around the block, turn back, but at some point you'll eventually reach my house. At the end of this kind of story, you'll have a mental map of the neighborhood where I live in, so when I invite you the next time, you might end up not taking any wrong turns and eventually getting there. So in general, such exploration and navigation behavior is pretty intuitive for humans, which is why we get invited to parties with vague instructions. But what would it take for a learning algorithm to enable this kind of behavior for our robots? To build a robot capable of exploring and navigating like this, we need to learn from a diverse prior data set in the real world that can capture a wide variety of skills and behaviors, as well as the environmental factors of variation. While it's possible to collect large data sets in the real world from demonstrations or maybe a systematic randomized policy, learning meaningful exploration behavior from this data can be really challenging. And it requires a robot to generalize to unseen neighborhoods, recognize visual and dynamical similarities, and form a representation of visual observations that's generally robust to weather conditions or, let's say, the color of the grass. For example, we're like a robot trained in the Berkeley Hills, which generally looks like this yellow mess on the left, to is a much harder and slower task, which requires your robot to actually drive to places in order to explore it. Since such factors can be hard to model in a simulator or transfer from a simulated environment, we tackle these problems by teaching the robot to explore using only real-world data. In this work, we present rapid exploration controllers for outcome-driven navigation, or Recon, which is a simple framework that combines latent goal models with a non-parametric memory, allowing the robot to explore and represent large spaces. Recon combines the strength of sampling-based exploration from the goal condition model, which can provide general purpose knowledge about navigational affordances as well as short-range control, with frontier-based exploration, which uses a topological graph and can be used to navigate to distant goals and learn a good representation of the map. We find that our approach is able to rapidly explore and represent the information necessary for navigation while relying solely on an offline data set of trajectories containing image observations with no expert demonstrations or annotations. So let's take a quick detour and talk about what a suitable data set for learning such behavior would look like. For the tasks in the paper, we develop on the robot you see here, which is a ClearPath Jackal ground robot, a pretty reliable robotic navigation platform. Open world navigation with unstructured terrain and obstacles is pretty hard to simulate, and that kind of pulls us away from the general approach of simulating, learning in simulator, and doing a sim-to-real transfer. As a thought exercise, if you wanted to do online reinforcement learning, say a visual navigation state-of-the-art baseline from iClear 2020, collecting the order of 1 billion frames of data would take me 2 years on a system like this, which has battery constraints, and you can only collect data like 6 or 8 hours a day, which, it doesn't sound that great. So what is feasible if you want to collect a real-world data set? Well, you want it to be large. You want it to be a large offline data set that has a lot of variety. You want it to be collected easily, and optimistically, it should be collected in an autonomous fashion so that you can kind of rest in the shade and not be too worried about it. And it should capture a wide range of appearance changes, scenes, weather changes, obstacles, and so on. To this end, we collected an offline data set of trajectories that can be used for learning exploration behavior. At the core of this data set is an autonomous data collection policy that uses a systematic random walk and a safety controller at the high level that uses a 2D LiDAR to automatically label trajectories that you've collected. In all, this amounts to about 5,000 trajectories in 10 to 12 different real-world environments. A small sample is shown on the right. which demonstrates considerable variability in the terrain, obstacles, general navigational principles in different environments, and so forth. The data was collected over a span of 18 months and 3 projects, showing significant variability in data collection preferences by the people operating, as well as weather conditions, and appearance due to rain, hail, or sunshine, or whatever subset of that we get in Berkeley. This dataset is a curation of autonomously collected random walk data, along with a small amount of rollouts from learned policies and expert demonstrations in critical environments, a truly rich dataset of interaction. We're publicly releasing this dataset on the project page and the link which is on the slide, and hope that it's useful for future research in both real-world robotics using offline datasets, but also just trajectory and video prediction problems in general. All right, so given a dataset like this, during training, we learn a context condition latent goal model from a pair of current and goal images. Our context condition model is trained to predict short-range temporal distances to the goal, as well as the best first action towards it using a variational information bottleneck. Because the training goals are short range, labels for these predictions can be easily obtained from any policy, including a randomized policy. We formulate the objective to retain only the information necessary for representing and reaching relative goals, which are on a short horizon. So by design, the overall representation is designed to kind of save itself from representing features that are not relevant to the task of prediction. Since we're compressing the observations, our representation is encouraged to only contain information salient to the task at hand and ignore information about appearance, weather, or obstacles that did not affect these distances on the short range. During deployment in a new environment, we use this learn distance function to incrementally generate a topological graph over a subset of observations. The robot can use these to efficiently represent the environment. I want to emphasize that in this case, we are using the data set in a pretty dumb way to just kind of learn distances and delta waypoints as the mid-level action space, and not exactly for high-level planning. Since this paper was published, we've been making some progress using more sophisticated offline RL algorithms to learn this problem more end-to-end, and in general, extract more juice out of the data. But in practice, kind of imitation learning works fairly well for the tasks that we're discussing in this paper. All right, so what does the exploration algorithm look like? We follow a hierarchical control approach where a high-level controller is informed by the graph and commands a sub-goal to the low-level policy. If the robot believes that the goal is reachable, it adopts the representation of the goal image as a sub-goal. The robot's confidence about this is based on the probability under the prior of CGT. As the robot updates its VIB prior, a highly probable goal embedding implies that the robot has learned to represent paths in the new environment and is able to reach the goal directly. This is kind of the exploit scenario in reinforcement learning. Otherwise, if the robot is at the frontier of the graph, it adopts an imaginary sub-goal sampled from the VIB prior. This is in line with a lot of work in exploration using imagined goals. It's kind of the scenario where the robot attempts to reach imaginary goals at the frontier of the graph to find new states that it has not visited in the past. And lastly, if it's somewhere inside the graph and not exactly at the frontier, it adopts one of the nearby edges of the graph to kind of navigate to the frontier, so it can quickly expand its coverage in the new environment. And at the end, we kind of add the trajectory and fine-tune all the models, update the graph, and keep going. All right, so let's look at a few examples. So when deployed in a previously unseen environment, Recon explores the environment. On the right, you see an egocentric observation and a top-down view at the bottom left, which is not provided to the robot. In search of the target environment, it uses sampled goals from the latent goal model and builds a topological graph of this environment. At some point, it's going to find the goal. Yeah, there it is, and then it drives straight to it. Using about 20 minutes of environment interaction, Recon can build a topological map, which is shown by the white nodes here, and the path in cyan is the path it took while exploration. Eventually, it can plan through this map and find a more direct path to goal, for example, the one shown in red. And here you can kind of see the recovered path, and it takes about 10 or 15 seconds in the end to kind of go right straight to it. We now show some more qualitative results in other environments. For example, this parking lot scene, where the target is a red car, the goal image you see on the left, and it's completely out of sight. The robot's kind of explored the environment in the past, and it's trying to find a path that leads it straight to the red car. found it. There's a few more of these, but we can kind of skip to some more interesting stuff. So in the interest of time, some baselines. Okay, so an important characteristic of reliable open world navigation system is robustness to kind of appearance changes and seasonal changes and dynamically evolving environments which have new obstacles you haven't seen in the past. To examine this, we deploy Recon to find this blue dumpster in a junkyard. And this is kind of just the baseline case where it's the path that is discovered. It's a 5-second path, a few meters away, not too hard. We then perturb the environment with unseen obstacles. And to be specific, these are obstacles that it's never seen in the training data at all, like a car, some traffic cones, and trash cans. We see the Recon can demonstrate reactive avoidance in the presence of these obstacles and still successfully reach the goal. We also test its response to varying visual distractors due to appearance. In this case, rainy weather, sunny weather, and sometime around twilight. We generally, Recon performs really well, and we hypothesize that the information bottleneck learns a compact representation by discarding visual distractors, like lighting changes, and enabling kind of the success of Recon. Let's quickly go over some key takeaways before I wrap up. Learning from large offline data sets is a great way to enable capabilities in open world settings like the outdoor navigation setting we discussed earlier. We release a data set to facilitate further research in this direction. Latent goal models with a context condition architecture are very capable and can give us a good relative representation of goals. They enable local exploration by sampling from this representation and also enforce robustness by using compression objectives like the information bottleneck. And lastly, the topological map is a great backbone for efficient memory storage and planning, while also providing some high-level exploration cues. And yeah, I guess if you're wondering, that means robots can join us in the parties, if there are any. That's my time. For more details about the algorithm, experiments, and the data set, please stop by my poster at 11:30. And you can find links to the data set release, the full text, blog post, everything at the project page that's on the slide. Thank you.
We have time for one question or maybe two quick ones. Anyone in? Go ahead, Tingnan. I'm going to repeat the question. The question is, how do you represent the topological graph? It looks like it's a key component.
The topological graph is actually pretty explicit. So you have a latent representation of your images, which is, let's say, a 32-dimensional embedding, and then you have a learned distance function, which you get from your goal condition model. And your graph is basically just those vertices and the edges that are by the distance function. So yeah, nothing too fancy there. Yeah, there's no GPS. It's only images.
Before we go to another live question, are there any on the virtual audience?
I don't see any.
Okay, go ahead.
Okay, thank you. I'm just curious about multimodality. So in your example you started with, the homes may all look very similar, but just have a slight difference, which might be the number on the door. So I'm curious how your system adjusts to that, where you may have many dumpsters, but you're looking for a very specific one. And also if you could just say a little bit about some failure modes.
Right, so.
So I'm just going to repeat the question really quickly. The question was about how would you distinguish between maybe small changes like a number on a door and then also failure modes?
So I think the biggest problem with the way it's been presented right now is we focused a little too much on sticking purely to images, and the problem with that is aliasing. So especially in an example like London, all houses look the same, which is not great. And there's no real good way to handle it apart from saying that we add more data. So this data could be in terms of language, like adding instructions or GPS as a rough cue. We've done some experiments of adding kind of more multimodal inputs where kind of one predicts the other, and then you have a lot more of this. But yeah, in general, like kind of sticking with images, the aliasing is kind of inevitable for us. The second question, can you repeat that actually?
Failure modes.
Failure modes. Aliasing, actually. We have, so I skipped some of the baseline comparisons, but there are cases, especially for the few other methods where, if two houses look the same, it's just going to find one of them arbitrarily, including our method does that sometimes. And that's just kind of the limitation of an image, which we can kind of get rid of if we use better cues.
Thank you, Dhruv.